So what I've done is I've rewritten the last reaction that we were talking about, the double displacement precipitation reaction. That's called the complete overall balanced equation. We can also be asked to write down the complete ionic equation, and that shows all the ions that actually exist in the solution. Remember, ionic compounds that dissolve do not stay together. So when we write barium iodide aqueous, in reality, we don't have barium iodide floating around in the solution. We have cations and anions. So the rule is, if a compound is ionic and aqueous, we break it down, we dissociate it. So this barium iodide is not going to stay that way. Instead, how it actually exists is the barium cation is dissolved in the water, and the iodide anion is dissolved in the water. But look back at the formula. Barium iodide has one barium and two iodides. So when this dissociates, this subscript 2 becomes a coefficient that tells us how many iodides we actually have. We go to the next chemical, sodium sulfate. Sodium sulfate is ionic and it's aqueous, so this will also dissociate. When this breaks down, the cation is sodium and it's still aqueous, and we have two of those sodiums from the dissociation. The anion is sulfate, and we only have one sulfate because we had one sulfate in sodium sulfate. On the product side, the first chemical we see is barium sulfate solid. That's the precipitate that does not dissolve in water. If it does not dissolve, it cannot dissociate. So we don't break that one down. We leave this as barium sulfate solid. And then the other product is ionic sodium iodide, and it's aqueous. And notice this one has a coefficient of 2. So if we broke down one sodium iodide, we would just have one sodium cation in solution. But because we have two of those, we have to have two sodiums floating around. Same thing for the iodide. Each sodium iodide forms one iodide when it dissociates, but that coefficient of 2 tells us we have two iodides. So in green, we have the complete ionic equation, which is more detailed than the overall balanced equation because it shows us what's actually happening in the solution. In the process of doing this, we did not have any liquids or any gases, but the rule is if you have liquid, it's going to stay as a liquid. It doesn't break down, it doesn't dissociate. And the same thing is true if you had any gases in your equation. So in order to dissociate something, it has to be ionic and aqueous. If it's liquid, if it's gas, if it's a solid, it does not dissociate. This green complete ionic equation is not the most useful equation. In many ways, the most useful is called the net ionic equation, which cancels out anything that's not participating in the reaction. So in this green example, if you look at the reactants, we have two sodium cations. And on the product side, we also have two sodium cations. So those are not participating in any chemical changes, those are spectators. We can cancel those out when we write the net ionic equation. We also have a spectator, two iodides on the left, cancel two iodides on the right. So what we're left with is this net ionic equation, barium 2 plus aqueous plus 1 sulfate aqueous forms a precipitate of barium sulfate. This is useful because it shows us where the actual chemical change is occurring. The fact that the sodium was floating around in the complete ionic equation, we cancel that out because it's a spectator, and we don't need to focus on the sodium if we're just interested in what the net change is. Some problems, the most useful form is the overall balanced equation, because this shows us everything that we mix together.